in the last video, we ended off discussing what section was this? Of course, the system overview and in general, the policy. Now let's remark on 3.3, continual transfer via surgery, which is definitely one of the more novel and thought-provoking aspects of the paper. So they had to do changes for 3 reasons, which required surgery. So think of surgery as just like making modifications to the model so that you can continue the training. So as we experimented and learned, we implemented changes to the training process, i.e. reward, structure, observations, etc., or even to the architecture of the policy neural network. So the policy neural network is the action heads here. So I don't think that you can like fundamentally change the LSTM in this case because it is 84% of the model. At least they didn't. That would be like a pretty substantial change. So it looks like that they did not do that. And secondly, over time, they expanded the set of game mechanics supported by the agent's action and observation spaces. They were not introduced gradually in an effort to build a perfect curriculum. Rather, they were introduced incrementally as a consequence of following the standard engineering practice of building a system by starting simple and adding complexity piece by piece over time. So what they're saying is, okay, don't think that we gradually made the action space more complex to have this curriculum learning in order to kind of put the model through the stages of grade school and eventually become a grade 12 student and graduate. It's literally just because they became better over time and added more features. And then thirdly, from time to time, there was a new Dota 2 version, and this made changes which would pertain to the mechanics, hero, item, map, and properties. And in order to play against human players, which is the entire intent here, then they must be playing on the latest version. This is quite a interesting dynamic. Like it motivates them to be as fast as possible, right? They took 10 months and they said that if they did another setup, it could take 40 months. You can imagine if they did a 40-month training setup, which was the case if they did not do surgery, then they would have also had to deal with 4 times the amount of updates and likely like 4 times the surgery. Maybe that's an exaggeration, but the fact that updates occur over time means that they were motivated to do this project as fast as possible, which wasn't mentioned in the paper, but I imagine this was like an implicit motivation for them. These changes the changes can modify the shapes and sizes of the model layers, which would be mostly the policy, once again, of the neural network that takes the actions, the semantic meaning of categorical observation values or other things. And when these changes occur, most aspects of the old model are likely relevant. Of course, they're not like revamping the entire thing and like changing 50% every time, but cherry picking parts of the parameter vector to carry over is challenging and limits reproducibility. For these reasons, training from scratch is the safe and common response to such a change. So what they're saying is that like, okay, even though most of the aspects are still relevant, still trying to integrate this is hard, and most people don't, they just start from scratch. However, since this was a multi-month process with high capital expenditure, which is to say like, having on average 500 GPUs for 10 months, that must have been expensive. Like if somebody wants to do the Fermi calculation for that, then put in a comment. This motivated the need for methods that can persist models across domains and feature changes. It would have been prohibitive in time and money to train a fresh model to a high level after each such change, approximately every 2 weeks. For example, they changed to the newest Dota version 8 days before playing against the world champions. And this would not have been possible if we had not continued from the previous agent. Imagine if they had to train from scratch 8 days before playing their title game. Okay, and the surgery can be viewed as a collection of tools to perform offline operations to the old policy model, pi theta, so pi being the model and theta being the parameters of the model, to obtain a new model, pi hat theta hat, compatible with the new environment, which performs at the same level of skill even if the parameter vectors pi, theta, and pi have different sizes and semantics. They just changed these, and I'm not sure how they're assuming that it performs the same skill, but that's what they're saying. And then we begin training in the environment using the new policy with the new parameters. In the simplest case where the environment observation action space did not change, our standard reduces to insisting that the new policy implements the same function from observed states to action probabilities as the old, which is to say like maybe there's an update which doesn't affect the policy at all. In that case, then they just like rename the policy, but in actuality, it has not changed. And they talk about this net-to-net style, didn't really grasp that, so I don't think you should either, or I don't think it's necessary. And in the end, they performed 20 surgeries, along with many unsuccessful attempts over the 10-month lifetime of OpenAI 5. Surgery enabled continuous training without loss of performance. and they discuss their experimental verification of this method in 4.2, which we'll see shortly. Okay, this paragraph here is quite awe-inspiring. Let's read it. OpenAI 5 is a single training run that ran from June 30th to April 22nd, 2019. So like, it literally almost became a 1-year-old child, which is impressive. And after 10 months of training, using 770 plus or minus 50 petaflop seconds per seconds times days. I didn't put in the effort to understand what this unit means, but I think it just means a lot of compute per day. It defeated the Dota 2 world champions in a best of 3 match and 99.4% of human players during a multi-day online showcase. In order to utilize this level of compute effectively, we had to scale up along 3 axes. First, we used batch sizes of 1 to 3 million time steps. This corresponds with what they said in the introduction, which was 2 million, grouped in unrolled LSTM windows of length 16. I can't tell you what an unrolled LSTM window is, I'm sorry. Second, we used a model with over 150 million parameters. So what they're saying is that they scaled. And finally, OpenAI 5 trained for 180 days, spread over 10 months of real time due to restarts and reverts. Oh, so what they're saying is that they did actually have some restarts and reverts over the 10-month period because, okay, let's do some 10 times 30 is 300. Okay, so there was literally 120 days where the model was down. I thought it was like a continuous run, which is what they kind of, I mean, this is a single training run, so that makes sense, but it's not continuous. And now they compare to AlphaGo, and they used 50 to 150 times a larger batch size, 20 times larger model, and 25 times longer training time. Simultaneous work in recent months have matched or slightly exceeded our scale. So what they're saying is that scaling is occurring because AlphaGo, began in 2016, even 2015 earlier, and this paper was published in 2019. All right, for human evaluation, OpenAI 5 played against numerous amateur players, professional players, and professional teams in order to gauge progress. We'll check out the list. Yeah, in April 13th, they beat OG. Okay, now let's talk about machine learning systems, which often behave poorly when confronted with unexpected situations. While winning a single high-stakes show match against a world champion indicates a very high skill level, it does not prove a broad understanding of the variety of challenges the human community can present. To explore whether OpenAI 5 can be consistently exploited by creative or out-of-distribution play, they ran this arena in which they opened it to the public for competitive online games from the 18th to the 21st. And in total, 5 played 3,193 teams in 7,257 games. I'm not sure why these numbers are different. Oh, okay, because they sometimes play the same team twice. Okay, I understand. And 29 teams managed to defeat OpenAI 5 for a total of 42 games. So let's just read this. This is kind of useful information. Human players often abandon losing games rather than playing them to end, like in chess where you forfeit, even abandoning games right after an unfavorable hero selection draft before the main game begins. OpenAI 5 does not abandon games, so we count abandoned games as a win for OpenAI 5. And these abandoned games, which were literally half, likely include some people who had to go for technical or personal reasons, so maybe their mom told them to shut it off. This is just a side note. And I think with respect to the 29 teams that did beat them, they don't mention like any analysis here. Maybe in Appendix L, they do talk about it. So I'm really interested in this. I might actually look at this after the video because I think the 29 teams probably did some actions which were completely novel and what do you call actions in Emma, which were like unbefore seen? I guess, just new data. I forget the word that, like outlier. They somehow found an outlier that the model had not seen before. And for this, it maybe like made the policy like misbehave. And this can also be considered in the case of Go, where certain models, of course, DeepMind would have corrected for this, but initially, if you just trained a model on professional games, if you start playing really bad, the model has never played against somebody that's bad and also starts playing really bad. So this is an interesting kind of thought experiment, or not thought experiment, but just fact that if you train a model to be really good, then it doesn't know how to play against somebody who's really bad, which is impossible for a human, because for a human, you have to be first really bad before you can be really good. But if you can just train a model with supervised fine-tuning to be really good, then it does not go through the path of being bad. With respect to ELO, they have this true skill thing. So I think this is worth talking about. True skill, first of all, is like developed by Microsoft for Xbox. So it's like just a measurement of how good you are compared to others. So to provide some context of how this corresponds to human skill, we mark the level at which OpenAI 5 begins to defeat various opponents from random to world champions. So random would be 0, and then hand scripted would be, I guess, 100. And you can see that OG was around 250. And note that this is biased against earlier models because the true skill evaluation is performed against the final policy and environment. I'm not sure exactly why it's biased, but they must be onto something. Even though earlier models were trained in the, I guess because the last model had a different environment than the first ones. This is my assumption. And that we believe this contributes to the inflection point around 600 petaflop seconds per second days. Around that point, we gave the policy control of a new action by pack and performed a major Dota 2 version upgrade. Okay, so I guess this point... are they talking about this? I think they're talking about this inflection point, perhaps around, if it's around 600. So there you go. And the rapid increase to skill 200 early in training is due to the exponential nature of the scale. A constant true scale difference, approximately 8.3, corresponds to an 80% win rate and is easier to learn how to consistently defeat bad agents. So I guess they're saying that in the beginning, like this learning rate is given, but this exponential nature here was because of an update that they made. Now let's talk about reaction time. So OpenAI 5 can react in 217 milliseconds, whereas typical human reaction is 250 milliseconds. So even though it's only acting every 4 frames, which I thought would be a handicap, this is still like much faster than a human, because if you think about it, if there's 30 frames per second, then a human is not acting every frame. Therefore, it's not in fact a disadvantage to be acting only every 4 seconds. And while human evaluation is the ultimate goal, they also had to evaluate their agents continually during training in an automated way. And they achieved this by comparing them to a pool of fixed reference agents with the known skill. I think we're repeating what we said in the figure caption. And let's move on to playstyle, which is difficult to analyze rigorously. But in terms of broad terms, they discuss the comments that people made with respect to the playstyle. And one really quick note here is that in real-time strategy games such as StarCraft, where the key measure is actions per minute due to the large number of units that need to be supplied with actions, in this game, it is reaction time. So yeah, real-time strategy versus, I guess, team versus team. I'm not really an expert of the different genres of video games, but there you have it. So first of all, early in training, OpenAI 5 prioritized large group fights in the game as opposed to accumulating resources for later, which led to games where they were significantly behind if the enemy team avoided fights early. And this playstyle was risky and would result in quick wins in under 20 minutes if OpenAI 5 got an early advantage, but had no way to recover from falling behind, leading to a long 45-minute loss. But as they improved, it evolved to align closer with human play while still maintaining many of the characteristics learned on. OpenAI 5 began to concentrate resources in the hands of its strongest hero, which is common in human play. It also relied on large group battles, applying pressure while holding a significant advantage, but also avoided fights and focused on gathering resources behind. So looks like it learned to play like a human over time. There are still differences though, but now let's discuss them. Human players tend to assign heroes to different areas of the map and only reassign them occasionally. But OpenAI 5 models the OpenAI 5 model moved its heroes back and forth across the map much more frequently. Furthermore, human players are often cautious with their hero when their hero has low health, but OpenAI 5 seemed to have a very finely tuned understanding of when an aggressive attack with a low health hero was worth it, which is really incredible. It's just to say that whereas humans are much more risk averse, this model was probably just completely unbiased, and was like, okay, if this is the given situation, then I don't care about risk. Will it be a positive impact or a negative impact for me to attack? And then it just takes that decision. It also tended to more readily consume resources, as well as abilities with long cooldowns, which take a long time to reload, while humans tend to hold on to these in a case of better opportunity arising later. Once again, risk aversion. Okay, so we're at 4.2. There's only a bit left, so just keep up with me. Validating strategy with a rerun. In order to validate the time and resources saved by our surgery method, they trained a second agent kind of afterwards from May 18th to June 12th, 2019, or to say like concurrently with the last month of the training on the other model. No, actually they finished the training on the other model in April 2019. So this was completely afterwards. And this only uses the final environment. So it's static. And they call this a rerun, which did not go through the surgery. And it took 2 months with this amount of compute. And this time frame is significantly longer than the frequency of our surgery changes, which happened every 1 to 2 weeks, which is to say like it was uninterrupted. As a naive comparison, if we had trained from scratch after each of our 20 major surgeries, the project would have taken 40 months. But in practice, they wouldn't have made as many changes if that was the case. Another benefit of surgery was that they had a very high skilled agent available for evaluation at all times, as opposed to having to retrain from scratch and not having access to that good agent when that process was happening. So this is good to just have a good agent to train against. And in situations where the environment is pre-built and well understood from the start, there's little need for surgery. So rerun took approximately 20% of the resources of OpenAI 5. If we had access to the final version of the game ahead of time, there would be no reason to start training on a different version of the game, but this is not the reality. Rerun, which is the one that happened after without any changes in surgery, improved beyond OpenAI 5 skill and actually reached a win rate of 98% versus the final version of OpenAI 5. So now we have like kind of an alpha 0, mu 0 type of instance here where the prior model is getting beaten by the new one. And they validated that the parameters, or I guess the model was able to reproduce the 5 performance and go beyond it. So that's when they stopped training, but they think that it could have gone even better if they continued. This process of surgery successfully allowed us to change the environment every week. However, the model ultimately plateaued at a weaker skill level than the from scratch model was able to achieve. So they kind of lobotomized it. And learning how to continue long-running training without affecting final performance is a promising area for future work. While surgery as currently conceived is far from perfect, with proper tooling it becomes a useful method for incorporating certain changes into long-running experiments without paying the cost of restarting every time. So in this graph, I'm not even going to look at the caption or the whatever it's called. Let's see what's happening. So we have the original OpenAI 5 graph from October to April or whatever it was. And then they have the rerun, which happened afterwards, right? So you can see has like similar growth, but then is able to go beyond. And then they have a simulated graph of the hypothetical always restart run, where for every single surgery, I think they said, did they have like 20? They would have had to, I mean, there's definitely more than 20 because there's at least 10 here, then 15 more. So that's at least 25. In each of these, they would have had to restart, right? So this means that you would have never got into the 200 and 250 skill range, which would have been very harmful to the reinforcement learning self-play regime. So this is just to show that this is the counterfactual, I guess, and then this is the rerun. Moving on to batch size, which is quite insightful. They evaluate the benefits of increasing batch size using some experiments. And this means two things. Either using twice as many optimizer GPUs to optimize over the large batch, or using twice as many rollup machines and forward pass GPUs to produce twice as many samples to feed the increased optimizer pool. One compelling benchmark to compare against when increasing batch size is linear speedup, which means that in theory, using 2 times as much compute gets to the same skill in half of the time. If this scaling property holds, it is possible to use the same total amount of GPU days and thus dollars to reach a given result, but in half of the time, since you're just doing more data you're doing double the data, right? In practice, we see less than this ideal speedup, which is a good reality check since usually things don't scale linearly as you make the parameters larger. But the speedup from empirically, of course, but the speedup from increasing batch size is still noticeable and allows us to reach the result in less wall time, which means the actual time that you have on the stopwatch. And they define the speed up as the slow time divided by the fast time. So if the slow time took 2 days and the fast time took 1 day, then you have a 2x speed up. The results of varying batch size in the early part of training can be seen in figure 5, which we'll see. And increasing batch size speeds up training through the regime we tested up to batches of millions of observations. Using the scale of rerun, they were able to reach superhuman performance in 2 months. And they had a 983,000 time step per batch size, as opposed to 123,000 time steps per batch size in their baseline, which is 8 times more samples in each batch size, only giving a 2.5 increase. So you can see here that is not linear because in this baseline linear speed up, you should have an 8x speed up if you increase the batch size by 8 times. Now they're talking about a smaller batch size, then we might expect to wait 5 months for the same result, which is to say that if they had not made the batch size 983,000, then it might have taken 5 months, which is still twice as fast as the original speedrun, which took 10 months. But nevertheless, they speculate that it would be longer than 5 months. Or what are they speculating here? Okay, if we had instead used the smaller batch size, then we might expect to wait 5 months for the same result. We expect that it would be slightly longer, as the speed up factor of 2.5 applies at true skill 175 early in training, but it appears to increase with higher true skill. So I don't know what they're trying to say here. Anyways, we hope to find in the early part of training linear speed up from increasing batch size. In other words, that it would be 2 times faster to train an agent to a certain threshold if you use 2 times the accumulated data, but the results set the speed up as less than linear. However, we speculate that this may change later in training when the problem becomes more difficult. I think they're saying that as the problem becomes more difficult, then the agent becomes more competent, and then the increases are better, but that's not what the graph shows. So once again, not really sure what's going on here. With respect to the compute costs in the ablation study, they did not tune hyperparameters either. So this is something worth mentioning. Like if you do scale the batch size, then you would expect that the hyperparameters also need to be modified in some extent. So let's talk about data quality. I think this is the last part of part 4. So the games, they can take up to 2 hours. And for this reason, it's unreasonable to do on-policy reinforcement learning, because if they waited to apply gradients for an entire rollout to be played using the latest parameters, we could only make one parameter update every 2 hours, in which time the gradients that would be obtained from training on the replays from those games would be stale and like irrelevant. Instead, our rollout workers and optimizers operate asynchronously. Rollout workers download the latest parameters, play a small portion of the game, and upload data to the experience buffer, while optimizers continually sample from whatever data is present in the experience buffer to optimize. And really quickly regarding the batch size, you can see that when you have, okay, let's go through the ones that I can first understand better. So we have measured staleness, which means how many times did you train on the same data point. So if you have 1, then it's here, I guess. And then 2, 4, 8, 16, 32, like literally if you train on the same data 32, then you're overfitting. So that's why the speed up is 0. So here you can see this. Actually, I think that was measured sample reuse. I don't know how they define staleness. Let's see. This run covers early training at a small scale, which means 8 times smaller than rerun. On the left plot, we plot true skill over time for each run. On the right, we plot the speed up to reach fixed true skill thresholds of 100 to 175 as a function of the parameter under study compared to the baseline. See equation 2. Okay. Yeah, I forget where they explained this. It might be later, which is, so let's just go and continue our reading. Early on in this project, they had rollout workers collect full episodes before sending it to the optimizer and downloading new parameters, which is to say that exactly what they said was not ideal or optimal, they did at the beginning. And this means that once the data finally entered the optimizers, it can be several hours old, corresponding to thousands of gradient steps, and therefore they were useless or destructive. But in the final system, they did send the data to optimizers every 256 time steps. And they're saying even this can be like too long of a delay. So they define some metrics, which is called staleness. And this means that if a sample was generated by parameter version n, which is every 256 time steps, and we're not optimizing version m, then we define the staleness of that to be m minus n. And we can see in 5b that increasing staleness by 8 versions causes significant slowdowns. Note that this level of staleness can correspond to a few minutes in a multi-month experiment. So it's still saying that like kind of these tooth comb changes can actually have a large effect. And their final system design targeted a staleness between 0 and 1 by sending game data every 30 seconds of gameplay and updating to fresh parameters approximately once a minute, making the loop faster than the time it takes the optimizer to process a single batch. So they're saying that every batch takes, or one batch is equivalent to 32 proximal optimization gradient steps, and that whereas it takes the optimizer, or not, it doesn't take the optimizer, whereas the optimizer updates every minute the parameters, they send data like every 30 seconds, which means that on average, every data point should only be reused half a time. If every 30 seconds you're sending data and then every minute you're taking that in, then this is like a 1-to-2 ratio. But In reality, the final system target sample reuse is 1. So there has to be some other parameter here that is kind of making this 1 to 2 back to a 1 to 1, which I'm not sure of. But let's discuss here. Because optimizers sample from an experience buffer, the sample piece of data can be used many times. And if data is reused too often, it can lead to overfitting on the reused data, of course. So now they have the sample reuse, which just means how many times was the sample used on the policy to train it. And if the optimizers are consuming samples twice as fast as robots are producing them, then on average, each sample is being used twice, and we can say that the sample reuse is 2. And in figure 5c, we see that reusing the same data even 2 to 3 times can cause a factor of 2 slowdown. So we have 2 here, and we're at 50%. So there's the factor of 2 slowdown. Where were we? If optimizers, yes. So reusing it 8 times may prevent the learning of a competent policy altogether. So if you reuse the same data point 8 times, then you're kind of screwed, is what they're saying. And these experiments on the early part of training indicate that high quality data matters even more than compute consumed. Small degradations in data quality have severe effects on learning. And check the appendix if you want to know more. And I mentioned in episode 1, if you watched long-term credit assignment, so Dota 2 has extremely long-term dependencies. Where many RL environments last just hundreds of episodes, they can last tens of thousands of time steps, where each time step is every 4 frames. Agents must execute plans that play out over many minutes, corresponding to thousands of time steps. This makes our experiment a unique platform to test the ability of these algorithms to understand long-term credit assignment. And in figure 6, where's figure 6? Okay, it's right here. We studied the time horizon over which our agents discount rewards, defined as H being the time horizon, and T is the real game time corresponding to each second, and gamma is the discount factor. So I already motivated this once in episode 1, but I'm going to do it again because it is quite a fragile concept. So what you're seeing here is the sum of the infinite geometric series, where gamma is between 0 and 1, of T plus T gamma plus T gamma squared plus T gamma cubed. If you'd like to derive this, you can. It's quite a simple kind of derivation where you put S, the sum is equal to this, and then you subtract by the sum multiplied by gamma. I just made you confused, so sorry, but if you want to motivate why this formula is equal to the infinite geometric series, then please search it up. All I'm saying here, though, is that this is equivalent to what I just said, so T plus T gamma squared. And if you think about this being the overall discounted reward, right? Well, since T is equal to the amount of time per time step, and this is summing up over all of the episodes in the future, then you can consider this as the amount of valued time steps, full valued time steps you're extracting from the rest of the game, which is to say, okay, we have our gamma factor of gamma, and it will determine how far we are essentially discounting rewards, where if you have a large, so if you have like a gamma really close to 1, then you're discounting rewards quite little. But if you have a gamma that's like 0, then you're discounting rewards. Oh, did I say that wrong? Yes. Oh, no, I didn't say that wrong. So if you have a gamma that's 0, then you're just multiplying everything by 0. So the only reward that you're considering is the first reward. So there you go. We have it straight. And together, when we combine our gamma time horizon with the time per time step, this gives us effectively the amount of time in the future that the model looks to make its decisions and consider the long-term rewards. So let's move on. This measures, this is what they're going to say. This measures the game time over which future rewards are integrated, and we use it as a proxy for the long-term credit assignment which the agent can perform. Essentially what I just said. I definitely need to improve my explanation of that. So if you want to ask me in the comments, I will happily elaborate. And this implies that our optimization was capable of accurately assigning credit over long timescales and capable of learning policies and actions which maximize rewards 6 to 12 minutes in the future. As the environments we attempt to solve grow in complexity, long-term planning and thinking will become more and more important for intelligent behavior. I realized that I skipped this important sentence, which is to say that resuming training a skilled agent using a long time horizon makes it perform better up to long horizons, which would be between 6 to 12 minutes. So let's look at this graph. Effect of horizon on agent performance. We resume training from a trained agent using different horizons, and they expect long horizon planning to be present in highly skilled agents, but not from scratch agents. So I think they anneal it to be actually larger over time. The base agent was trained with a horizon of 180 seconds, and we include as a baseline continued training at horizon 180 seconds. So there you have it. So they train the agent 180 seconds up to a certain point. Once they reach that, then they diverge the training and have the different future horizon. How did they phrase this? The different ways of integrating future awards through this time horizon, which is from 720 seconds, which I believe is 12 minutes, to 45 seconds. And yeah, once again, increasing horizon increases win rate over the trained agent at the point training was resumed, with diminishing returns at high horizons, which is to say like 360 and 720. They kind of overlap, so I don't think it's a statistically significant difference between them. So there you have it. When the model considers longer term rewards, then it will play better, especially since this game lasts 45 minutes on average. So if you're not considering 6 minutes ahead, then this is not good. In essence, when you have to collect resources or decide if to go for a fight, then looking forward in the future is important. All right, now with related work, I'm really just going to buzz through this. Using a combination of imitation learning, human games, and self-play, the AlphaGo paper just demonstrated a master level Go player. So this is like one inspiration. MCTS, multi-college research, during training to obtain higher quality trajectories was used. And this has happened in all of these games. Most recently, human level play has been demonstrated in 3D first-person multiplayer environments, professional level play in the real-time strategy game StarCraft 2 using AlphaStar. So that was the game that DeepMind tackled for their video game pursuit after Go. AlphaStar is particularly relevant to this paper. In that effort, which ran concurrently to ours, researchers trained agents to play StarCraft 2, another complex game with real-time performance requirements, imperfect information, and long-time horizons. The model for AlphaStar used a similar hand-designed architecture to embed observations and an auto-regressive action decoder with an LSTM core to handle partial observability. Both systems used actor-critic reinforcement learning methods as part of the observable objective, and OpenAI 5 has certain subsystems hard-coded, whereas AlphaStar handled similar decisions by conditioning during training on statistics derived from human replays. So both of them are like not derived through self-play, but whereas OpenAI's is hard-coded, the AlphaStar paper is statistic, and OpenAI 5 trained using self-play, while AlphaStar used a league consisting of multiple agents, where agents were trained to beat certain subsets of other agents. This still sounds like self-play to me, but there must be some nuance here. And the value network in AlphaStar observed full information about the game state, including observations hidden from the policy. And this method improved their training and exploring its applications to Dota 2 as a promising direction for future work. I don't think it's promising because you're kind of giving the model information that it shouldn't have. And of course, it would probably play better if that's the case. So there you have it. Distillation and imitation learning offer an alternate approach to surgery for making model changes in response to a shifting environment. In concurrent work, OpenAI has reported success using behavioral cloning for similar purposes. What you're saying is like, instead of having a model and then starting from scratch, you can train the new from scratch model with distillation at a much faster rate on the old model, such that the surgery is not required and you're just kind of learning from the previous model, which is now deprecated. And now in the conclusion, when successfully scaled up, modern RL techniques can achieve superhuman performance, yada, yada, yada. The key ingredients are to expand the scale of compute used by increasing the batch size and total training time. Even in 2019, the scaling laws were heavily under play. In order to extend the training time of a single run to 10 months, they developed surgery for continuing training across changes to the model and environment. And while they focus on Dota 2, they hypothesize that these results will apply more generally, and these methods can solve any zero-sum two-team continuous environment. That's a tongue twister, which can be simulated in parallel tasks across hundreds of thousands of instances. In the future, environments and tasks will continue to grow in complexity. Scaling will become even more important for current methods as tasks become more challenging. So really a foretelling paper about scaling, and I hope you enjoyed.